Hi, I'm Shao-Heng Ko. This work is with Kamesh Munagala. I'm assuming you all can hear me and see my slides. So one of the fundamental questions in auction theory is designing optimal auctions, or the auctions that maximize the seller's revenue. So when there's only a single item and a single buyer whose private value is drawn from a known distribution, the optimal auction is just a fixed deterministic price. But that's not the case anymore when we extend to more general settings. For example, the buyer may have a budget on the payment, and here I mean the budget is strict, a strict upper bound on the payment, and by public we mean the budget is known to the seller. Or they may have a deadline and need to get the item before the deadline. Or even more generally, the buyer could have a private budget where the value and the budget can be arbitrarily correlated, which, as we'll see later, captures both the two intermediate settings. Now, these kind of settings are often called interdimensional in the literature because the type space of the buyer is more than just a single dimension of values. And it is known that the optimal auctions for these settings require randomization or lottery. And we can also think of these lotteries as letting buyers choose from many options on a menu, where each option has a price and a probability for getting the item. So as the settings become more general, we may need a large number of options, and this number can sometimes be exponential in the number of deadlines or budgets. Now, recently, there's a line of work on adding an intermediary or a third party to the plot. So let's assume no budgets or deadlines for now. So we just have a seller selling a single item to a buyer. And in this example here, the buyer's private valuation is either 1, 2, or 3 with equal probability. So it's a discrete prior. And here, the optimal auction is simply a take it or leave it price of 2. Now, imagine there's an intermediary who can observe the buyer's true type. But before learning the true type, the intermediary designs a signaling scheme, which just regulates how they can send signals to the seller. So for a concrete example, this is a signaling scheme with two signals, the blue one and the green one. So this is saying that given the buyer's private value is 1, the blue signal is sent with a probability of 5/6, and the green signal is sent with probability 1/6. So same goes for the other types. Now, this information is sent to the seller. So if the seller receives the blue signal, they can do Bayesian update, and their posterior will look exactly like the blue distribution here. So now the probability that the buyer has value 1, conditioned on receiving the blue signal, becomes 5/9. So just to remind again, this scheme is designed before the intermediary can actually see the true type of the buyer. Okay, so its intermediary designs a signaling scheme, and then intermediary observes the type, and then signal sent to the seller. So now the seller would want to design an optimal auction separately for each signal they may receive to leverage the extra information. So given the signal, they proceed to implement the optimal auction for the signal. And the optimal auctions for each signal can actually be different. The buyer then reacts to this auction, and the item may or may not sell. So some intuition about this process. First, we know that the seller can choose to just ignore the signals, in that they can just stick to the optimal auction for the prior, regardless of what signal they receive, which will give the seller the original revenue. And of course, they sometimes can do better with this extra information. So in general, adding this intermediary cannot hurt the seller, but may hurt the buyer. And at the very extreme, if the signal just reveals the buyer's true type, then the buyer gets nothing. But here's a striking result due to Bergman, Brooks, and Morris in 2015 that says one can actually make the buyers better off with such an intermediary as well. So specifically in a setting without budgets or deadlines, they showed that there is always a signaling scheme that can guarantee the item always sells. And because we usually assume the item holds no value to the seller, this means the expected social welfare is maximized. And secondly, we just argued that the seller can at least get the original revenue. And this scheme makes sure the seller gets exactly that and nothing more. In other words, the seller's revenue under this scheme is the minimum over all possible signaling schemes. Now, putting these two properties together, it implies the buyer surplus, which is exactly the difference between social welfare and the seller's revenue, is maximized. And therefore, we call such scheme buyer optimal. So let's now see the buyer optimal scheme on the example we just saw. Without signaling, the optimal auction for this prior is a fixed price of 2, and the expected revenue is 4/3. The key ingredient in their construction is to use equal revenue signals. So what does this mean? It basically means that in every constructed signal, the seller is indifferent between setting any of the values in the support of that posterior as the fixed price. So concretely, the example shown here has 3 signals. And in the blue signal, the posterior distribution includes all types of buyers with value 1, 2, and 3, with probability 6/12, 2/12, and 4/12, respectively, as shown in the figure. And we can verify here that setting a fixed price of 1, 2, or 3 all gives the seller the same revenue of 1. And same goes for the other signals. For example, the brown signal has buyers with value 2 and 3, and the sellers indifferent between setting a price of 2 and 3, and so on. So as such, we can also verify that the total expected revenue that the seller gets from all the signals, when aggregated together, indeed equals the original maximum revenue 4/3. Now, because the seller is indifferent among the prices, we can suggest setting the price at lowest value in each signal, which will then lead to efficiency. In other words, the item will always sell. So this scheme satisfies the desired properties and is buyer optimal. And note that here the equal revenue signals are unique given the support set and doesn't depend on the probability values. So given such a powerful result, the question we're trying to answer in this work is whether or not it can be extended to more general settings. So specifically, is there also a buyer optimal scheme when the buyer has budgets or deadlines? So here's a summary of our results on answering this question. We found the answer to be yes for both the public budget setting and the private deadline setting. And furthermore, we propose a framework that unifies the positive results altogether by reinterpreting the signaling as a continuous process so that the same plan of attack can be used for multiple settings. This is the main technical highlight of our work, and it will also be the focus of this talk. On the negative side, we found the answer to be no for private budget, so there may be no buyer optimal schemes when the buyer has a private budget. So let me introduce the idea behind our continuous time framework. Instead of thinking the signaling scheme as a function that just maps the prior to the signals, we think of it as a continuous time process in which probability masses of buyers are gradually moved from the prior to the signals. So at any time during this process, there's always some signal being continuously pulled away. And under this view, we identify 2 properties such that satisfying them both will ensure the scheme being buyer optimal. First, for the signal currently being constructed, its optimal auction needs to be efficient. And second, the revenue of this optimal auction needs to match the loss of the optimal revenue that the seller can get out of the residual prior. And by residual prior, we mean the collection of the remaining probability masses in the prior. So if this is true throughout the course of the process, then the total revenue across the residual prior and all signals is always preserved, so that at the end of this process, the total revenue across all signals is exactly the original revenue. Now, up to this point, we have not specified the setting. So the fact that these properties lead to buyer optimality is not a function of the specific setting. However, finding the construction of signals that satisfies both properties does rely on the specific setting. And it's the second one that is especially tricky. So to argue the second property, we need to analyze both the optimal auction for the constructed signals, as well as the gradient of the revenue for the rest of prior. And this is not easy since the optimal auction for the rest of prior can actually change at any instant. So to clear this hurdle, we need to show that for the right construction of signals, the optimal auction doesn't actually change unless the support of the rest of prior has changed. So this allows us to break down the entire process into discrete portions, each with a fixed support set of the rest of prior, and relate the two optimal auctions together. And of course, this is just part of the deal since we also need the optimal auction for the constructed signals to be efficient. So naturally, these two parts are setting dependent. So for the public budget setting, we actually show that the construction for the setting without budgets or deadlines is already enough for the purpose. But this does not extend to the deadline setting. And in fact, since the buyer type space is richer in the deadline setting, the old construction is not even well defined there. So our second technical contribution is that we propose a new construction of the signals that takes into account the deadline dimension and prove that it satisfies both requirements. So it also leads to a buyer optimal signaling scheme. Now, before I briefly introduce our construction, let me give more details of the private deadline setting. So in this setting, the buyer has a private deadline in addition to their private value, and the item has no value to the buyer if they don't receive it in time. And it is assumed that the buyer cannot strategically misreport a later deadline, but they may exaggerate and report a tighter or earlier deadline. And this setting is also coined the FedEx setting in the literature. For this setting, it is known that the optimal auction only awards the item to the buyer right at their personal deadline, if at all. And roughly speaking, the price is going to be the highest for the tightest or earliest deadline, and then gradually decreases for later deadlines, such that the entire auction looks like a downward ladder of prices. And this also mirrors that in e-commerce, the fastest shipping option is usually the most expensive. Now, I won't have the time for the details, but let me informally introduce our construction for the deadline setting. Our task here is to define a signal given the support of the rest of prior, which has a value dimension and a deadline dimension. So we define the notion of lower envelope on this support set as a collection of types that look like a boundary of the entire set, so that roughly speaking, there's no buyers with lower value or lower later deadline than this set. And the good thing about this lower envelope is that it creates a mapping from the value to the deadline. So the equal revenue signal based on this set is unique. And that's what we use in our construction. Importantly, it remains true that the optimal auction for this signal is still a posted price at the minimum value. We then prove that the optimal auction for the rest of prior does not change from pulling away these kind of signals, so which will again give us the revenue equality. Now, a few words on why this doesn't extend to private budgets. When the buyer has a private budget, their payment cannot exceed the budget, and the buyer is also prevented from over-reporting the budget, but can still strategically under-report a smaller budget. So this is actually just a deadline setting plus a constraint that says price cannot go over the budget. Now, so because the deadline setting and the private budget setting, because the type space, the dimensions of the type space align, it is actually intuitive to use the construction for deadlines on the private budget setting. But turns out, although one can still do the overlap envelope and create the equal revenue signals on that, they just don't satisfy the efficiency property anymore in the private budget setting. And actually, the optimal auctions for those signals are no longer just posted prices, so we lost the efficiency property. In general, we prove that for certain instances, no signaling scheme that guarantees efficiency can approximate the optimal consumer surplus to any non-trivial factor. And even if we sacrifice efficiency, the best we can do is still just roughly a half approximation of the optimal consumer surplus. So let me briefly recap our results. So for the public budget and private deadline settings, we showed the existence of buyer optimal signaling schemes using our continuous time framework. And the optimal auctions for these signals turned out to be just simple posted prices. And this is in stark contrast to the general manual complexity of the optimal auction for the corresponding settings. And in hindsight, these two settings are such that the optimal auctions satisfy exposed rationality, which means that the buyer pays only if they receive the item. In contrast, our negative results critically require interim rationality, where the buyer pays a price before knowing whether or not they receive the item. And currently, we still don't know if there's a buyer optimal signaling scheme under exposed rationality for the private budget setting. We also don't know if there's a constant factor approximate scheme if we don't require efficiency. And if so, it would give us a positive counterpart to our lower bound. Last, we have not yet exhausted all the possible settings in its scope. So for example, our framework could apply to other extensions of the deadline setting, like the single-minded agent setting, where the relations between types are partial relations instead of being linear. And that would also be non-trivial since it would again involve some characterization of the optimal auction for the specific setting. So that's my talk. Thank you, and I'm happy for any questions.
Thank you very much. So it does seem that private budgets makes our life much more difficult throughout these talks. Are there any questions? Maybe virtually? All right. Okay, if there are no more questions, let's give our speakers another. Oh, there is one. Okay. Can you maybe move to the microphone?
So if you are looking at constructing signals so that you need to look at where the support or the distribution changes, does that mean that your results only hold for G with discrete support, or can you just can you handle continuous supports by discretizing sufficiently finely and then applying your results anyway? That makes sense.
Thanks for the question. Actually, like what you said is true. Our techniques critically needs the support set to be discrete. However, so if we are dealing with continuous support or continuous prior, we need like different techniques for it. But that said, we also know from the related work that we can almost always approximate continuous support with a very fine-grained discrete support, so that the revenue and everything is going to be approximated. So that's one way of thinking about it. But to answer your question directly, our technique cannot deal with continuous support.
I don't see any other hands raising or any other questions. Thanks again for attending. Thanks to all the speakers. Let's give them another round of applause. And we now have a break before we have another plenary session in the other room, in the other building.